So today we're going to move on to chapter 8, where we're going to talk about bivariate data. As the word bi suggests, we're looking at data where two measurements are taken for each observation. Essentially, we want to apply the principles of chapter 7 to two data sets at the same time. Changes things a bit, well, sort of significantly, but once you sort of figure out how to do it for two data sets at a time, you can do it for 3 and 4 and 5. It's actually easier to generalize from the two-dimensional case to higher ones, but we're actually not going any higher than this. Like 2 things at a time is the most we're going to be doing in this class. So, and you know, sort of keeping up with our theme, we sort of want to know, like, why would we actually do this? It turns out that sometimes when we want to answer questions about something, it makes sense to take more than one measurement to get a proper judgment, right? So you can imagine if I were to judge every student in this class by one of their grades, that probably wouldn't be a good thing, right? It wouldn't be a good estimate, right? If I picked that quiz that you did the worst on, it's not exactly going to be an accurate depiction of your qualities. So what I do for each student, I can look at several grades, right? For each observation, I make several measurements, right? So the idea of doing statistics where you can take several numbers into account in different categories and consider that all at once is going to be an important thing, because it comes with decision making and answering questions. Sometimes you need more than one measurement to properly judge what is happening. So in chapter 8, we're going to extend what we learned from chapter 7 and try to somehow generalize that to cases where we are taking 2 measurements at a time, right? So instead of 1 grade for every student, what happens if I look at 2 grades for every student, right? How do things change? Does the standard deviation change? Is there such a thing as a standard deviation anymore? What does it mean to be an average in that case? All these things, everything that we figured out that we needed in chapter 7, what happens when we sort of add another data set and we want to consider it all together at once? How do things change? That's what chapter 8 is going to be about. And in chapter 9, we're going to get into the serious math with this. Chapter 8 is sort of an introduction. It's going to give us all the definitions and principles that we're going to need to actually do the math. And in chapter 9, we're going to do the math. So that's sort of where we're going with it. So that's the idea. So let's start with pictures. Remember, we said why these are important last time in the chapter. Sometimes looking at a pictorial representation, a chart, was very instructive and it didn't bog us down too much with useless information. So we're going to start with the pictures. The typical one here is the so-called scatterplot. So we're going to sort of start to examine this chart to sort of figure out what the rules of our game is. Scatterplot. Right? So this is basically plotting 2 data sets on a Cartesian axis, right? So basically the same like the x and y axis that you're familiar with, that's what we're going to do. Each point of course, has an x-coordinate and a y-coordinate, right? And we just associate these with the two measurements, right? So the first coordinate can be the first exam grade of a student, and the second coordinate would be the second exam grade for the same student, right? So each point gives us two measurements, right? That's sort of the idea, right? So let's actually just jump right into an example, because I think it's sort of straightforward. Make a scatter plot. For the grades. The students. Two different exams. So, okay, so here we are, exam 1, exam 2, and here you can think of like the student number. All right, so I have student number 1, student number 2, student number 3, student number 4, 5, 6, 7, 8, 9, 10. Right? So I just order the students, and some can be in order, maybe by alphabetically their names. And I'm going to list 2 grades for every student. We're going to come up with a chart and sort of figure out, is there some way from this chart to figure out what an average is, or some idea of how the spread is and all that stuff that we figured out last time? Is there a way to generalize it to here? So let's say this first student got a 51 on the first exam and 70 on the second, 57, and 54, 62, 58, 64, and 68, 73, and 83, 77, and 60. 79, and 74, 82, and then 88, 92, and then 95, 98, that's a 98, hopefully you can see that, and this one is a 96. So it got squished up there. So basically we're going to define our variables. Let X be the exam 1 grade, Y be the exam 2 grade, and we are going to plot a picture called a scatter plot. So I'm going to plot the X versus the Y. And you plot it how you think you plot it. Think of these as a coordinate. This is the X coordinate versus the Y coordinate. So I can have, say I put a, so let's say I put 50 here, 60, 70, 80, 90. 100, 50, 60, 70, 80, 90, 100. So the first kid got a 51 on the first one and a 70 on the second. So he's going to be roughly like here. That point actually represents the first student, right? So that's, just by looking at that data point, you automatically know 2 measurements at the same time, right, for each observation. This student got a 51 on the first exam, a 70 on the second, right? So we can get 2 measurements at the same time. Right? And we continue in the same fashion. So we go from a 57 roughly to a 54. So the second student's going to be somewhere like here. Then we're going from a 62 to a 58. Right there. Then we're going from a 64 to a 68. Here. And we're going to go from a 73 to an 83. Then we're going to go from a 77 to a 60. Then we're going to go from a 79 to a 74. Then we're going to go from an 82 to an 88. Then we're going to go from a 92 to a 95. Then we're going to go from a 98 to a 96. So this chart here, this picture is called a scatter plot, right? Because you have points scattered all over the page, right? That's the idea. So it's called a scatter plot. Now, if you look at this kind of table, right, you're given this kind of data. What are some of the questions you want to be able to answer? Sorry,
Average.
What's the average of the class? Is it doing better overall, or are they getting better as time goes on, or are they getting worse as time goes on? Questions like that are what you'd want to be able to answer, right? So how does a scatter plot actually help us answer these questions is going to be the question of the day. And we're going to use sort of the scatter plot to sort of figure things out of what it means to be an average or a trend, right? Are things trending upwards, right? So would you assume that the students are on average doing better for this one? Just by the picture. What do you think about this class? On average?
Yeah.
Sort of, right? You sort of see like the points are slightly going up. There are a lot of students who actually did worse on the second one than on the first one, but overall the trend seems like, things are going up, right? And we're going to sort of discuss what this means, right? But that's called a scatter plot. This is basically what it means. So for each observation, we're taking two measurements and we plot it on an x-y axis. Each coordinate represents an observation with two measurements, and that's the scatter plot. So this is the scatter plot of the 10 grades. Now let's sort of ask ourselves, what's the pattern here? And can we somehow formalize it? To talk about it in a math sense. It turns out the answer is yes, we can. And then let's do it in terms of the means. And for each mean separately. So I'm going to look at x bar and y bar, the average of the first exam and the average of the second. So let's actually find it here. Did I actually compute these? I don't think I did. I sort of spoke about this in January. But I guess I'd want to illustrate it with this one. Does someone want to find the average here? X bar is, and y bar is, okay, So now what we're going to do is we're going to want to sort of split this graph up in terms of these averages, right? So our first average was a 73.5. So let's say we have 73.5 for the x. This is the x bar. It's going to be roughly 73.5, right? So that's like the line representing the x bar. And then there's going to be a y bar, which shows that that's roughly 74.6. So this line here represents y bar, right? So this is y bar, and this is x bar, right? Now you'll notice something here. I just split our picture into 4 parts. Now what does that mean, right? What is sort of a pattern that you see when I split the thing like this? What can you tell me about these? Like if I call this region 1, and call this region 2, call this region 3, call this region 4, what are some patterns that you see? Go on, say anything. Anything that jumps out at you about the pattern.
Most line 3, 2.
Right. Most of these points are in 3, 3, and 2. Right? Notice that there's hardly anyone in region 1 or region 4. Right? That's going to be, that's one pattern. Right? Just, it's not a trick question. It's just say whatever looks obvious to you, and we're going to actually make sense of it in terms of math. Right? So, okay, so most things end up in those regions. So how do we actually capture this idea? The pattern is most points end up in regions 2 and 3. Let's try to capture what this means. Remember last time when we were looking at means, we sort of developed the standard deviation, right? This sort of the spread when it turns out we're looking at means. And what we did was we looked at the difference between each value and the mean, right? So we're going to look at the differences xi minus x bar and y minus y bar and let's also look at their product, right? If I take each x minus x bar times y minus y bar. So we're going to look at those guys, and you're going to see why we care about that before. It's very simple. So this is very similar to what we were doing with standard deviation. We looked at the average distance between the values and the means, right? I'm doing that same thing here again. Right? So now, what can I say about, I numbered the regions. So what can I sort of say about the signs here, right? If I look at x minus x bar and y minus y bar and the product x minus x bar times y minus y bar, what would be the signs of these? What would x minus x bar be? It would have to be positive, right? If a point is here, no, x minus x bar. Remember, x is here, right? Which means the average x is here, which means you're in this region, you're to the left of the x's, right? So it means the sign of this would actually be negative, right? So this would be a negative sign. Because any point over here is less than, the x value of any point here will be less than the average x here, right? So that sign would be negative. What about the y's? This is where the average y value is. So if your point is here, is it higher or lower than the average y? It's higher, right? So if I take y minus y bar, what do I get? I would get positive. So what would the sign of this be? Negative. Okay, that's going to be an important pattern, right? We're trying to capture the patterns in terms of numbers, right? What about here? If I look at x minus x bar, and y minus y bar, and I look at x minus x bar times y minus y bar. And x value is over here, and the average x is here, which means this x value is lower than the average. So this means
Negative.
this is negative. What about here? The y minus y bar.
Negative.
It's also negative, right? Because the y coordinate of any points down here are smaller than the average y coordinate. So then I take a negative times a negative, and I get positive. Right? What about over here? I look at x minus x bar, y minus y bar, and the product. This one? Positive. This one?
Positive.
It's also positive. So this?
Positive.
Positive. Down here?
Negative.
We're working towards something. We're going to get a formula out of this yet. So it's not a pointless exercise. We're going to see it come together soon. Okay, this? That has to be positive. Negative, right? Because the y coordinates here are below the average y coordinate. So this is negative, right? So in some sense, in this way that we're sort of setting things up, this would sort of be, in general, a negative region, right? Where this will be a positive region, where this will be a positive region, where this will be a negative region. Right? We're sort of doing like the beautiful mind thing, you know, when he looks at physical reality, sees all these equations in his head. That's what we're kind of want to do, right? We want to look at this picture and see pluses and minus signs, right? And we're going to like develop things from that, right? So the idea is this region and this region is in some sense to us the negative regions. This region and this region in some sense to us the positive regions, right? Therefore, it takes into account if most things fall in here and here, then I can say overall the scatter plot has a positive trend, right? If most things fall here and here, I can say overall has a negative trend, right? I want to be able to describe things in terms of signs, right? So, on average, by that I mean the mean average, if most points into regions 1 and 4, there seems to be a positive trend. Most points it's 1 and yes, I meant 2 and 3. 2 and 3 goes with the positive, and 1 and 4 goes with the negative. 1 and 4 have a negative trend. Right? Now, as of this point, positive trend and negative trend are really vague terms. We're going to make it precise, right? We're math people, so we have to be super precise when we say this, right? So, what does it mean? Meaning. I drew 2 examples. So imagine I have 2 data sets, one looks like this. Right? You see that most points are in 1 and 4, right? And the other one looks like this. Right? So this is an example where most points are in 3 and 2. Right? Now, if you sort of wanted to see how on average the points are behaving, what you can do is you can draw a line. Right? Try to connect a path that all these points are following. So you can sort of draw a line that sort of stays close to all the points at the same time, on average. And what do you notice about this one? Right? The trend line, again, we're going to make all this precise soon. I'm just sort of giving you the intuition. Has negative slope. While here, notice that the trend line, right, this line that sort of describes how the points are moving on average, it has positive slope. So basically when I say something has a positive trend or a negative trend, it means if I draw a line that connects most of the points, the line will have a negative slope or a positive slope, right? In relation to these things, right? That's what I mean by trend. Later on we're going to call this like as a negative correlation versus positive correlation. We'll talk about that soon. So you sort of see the idea. We have this data that's given to us in sort of 2 dimensions. You plot it on a graph and now we want to see the patterns, right? So we were sort of looking, how do we make patterns of this in the math sense, right? Well, so we're trying to, how do we assign numbers and signs to these things? And we sort of took our cue from the standard deviation. We looked at the difference between the points and their means. And then we sort of developed a kind of sign chart where we can say, oh, this guy is sort of the negative region, that's the positive region. And it falls in line very nicely with what we know about straight lines, right? Positive slope versus negative slope. This idea is going to be a very important idea. And being able to actually compute exactly what this line is also going to be very important. It's going to help us with prediction, which if our math doesn't help us predict things, it's what use is it, right? So you can sort of see where we're going here, right? So here, notice on average, if I look at the product x bar and y minus y bar, on average here it's negative. Here, on average, x bar, y minus y bar is positive, right? Now there might be guys that don't follow the pattern. Sure, that's fine. But I'm talking about on average overall. So when I say on average, I mean, of course, the mean average. So saying on average, this product has a certain sign, what am I actually saying? Well, on average indicates we can take the mean of such numbers, which is going to lead us right into our first formula. That we shall call the correlation coefficient. Do you see what the correlation coefficient is? It's a number that looks at the average of these. Right? So, definition. The correlation. Right? Correlation means the relationship they share together, right? The correlation coefficient of variables x and y is denoted, this is the symbol, by C with sub xy, so we go, and is defined as Cxy is equal to x1 minus x bar times y1 minus y bar plus x1, x2 minus x bar times y2 minus y bar plus xn minus x bar times yn minus y bar. And we actually take the average. So yn minus 1, we're sort of looking at as the standard deviation kind of average. Do I want to erase this? Or am I going to need that picture? By the way, for the grades I did compute average, I think y bar was supposed to be 73.6, not 74.6. That's what I wrote here. I came back to that example and I computed it. So probably go back and change that. So for the original data set I had here that I erased, the x bar was 73.5, the y bar was 73.6. Yeah. Okay, so make sure you correct that. So let's continue. Okay, so boom, boom, boom. Here, n, where n greater than 1 is the number of data points. 74? Data points in the data set. Example. Well, that sort of sucks. I did all my calculations with 73.5 and 73.6. I'll have to double check that. I thought I even used Excel to double check this. Maybe I typed the wrong number. Okay, so here we're using x bar equals 73.5. Y bar equals 73.6, because those are the numbers I've used, so you don't want to have to compute all this again. This means that Cxy is equal to, you're going to take each data value, subtract their mean, and add all the products. So the first value was 51, subtract 73.5, times 70, subtract 73.6, plus, you're going to pair all these numbers. Take the x value minus the average x value times the y value minus the average y value. Divide that. There were 10 data points, so we're going to divide this by 10 minus 1. And this will give you, if you compute it all, which I've already done for you, 63.22. Note, this is a positive number. Right? Kind of leading towards the idea that we had before. There was some sort of positive trend. If I connected a line to get as close to all these points as possible, it should have a positive slope. So I'd expect a positive number here. That is called the correlation coefficient. This is a very important formula to know. You will definitely need to compute this on some test or exam or quiz. Right? So it's very important to know this formula. This is the correlation coefficient, it's called. And it's sort of looking at what regions the points end up on average, right? So on average, do they follow a positive trend or a negative trend? This number will tell you based on whether it's positive or negative. In the picture that I drew in this first example, it was sort of obvious, but a lot of the times it won't be obvious. Sometimes to count all the points, it's not going to be obvious. So what we do is we compute this number, and it tells us. Right? Now, oh, sorry, this was not the correlation coefficient. I wrote them down. This is called a covariance. Very sorry about that. Covariance. Didn't get a lot of sleep last night, obviously. Okay. Definition. Now I want to talk about the correlation coefficient. Now, normalize just means you want to care about the signs that you don't have to worry about scaling. It means just like in the last example that we finished in the last class, we realized that if we change the data points, like if we multiplied all of them by a certain number, or if we added a certain number to all of them, it could change things. We know that scaling actually affected the standard deviation, right? So sort of if I scaled all these points, this number changes all the time. We sort of don't like that. We sort of want to be able to scale things and still have our trend number be the same for various reasons, because we're going to be using it in calculations all over the place. We don't need this number changing on us from step 1 to step 2. We have to use a different number if we have to scale things, right? So we don't like the fact that scaling the numbers will actually change the covariance. So we actually want to find another number related to that, that when we scale it, this number actually remains the same. So it will remain the same in all steps of our calculations, right? So this is denoted by the letter R, and is defined as R is equal to CXY. While we do this, you're going to see a property here for the variance data. R will always be in this range. There's some more properties I'm going to say afterwards, but that's something that's very important. In fact, in the syllabus, I mentioned this. Right? It's one of the mistakes that you should never make. Right? Never give me an R value that's outside this range. You'll be punished very heavily for it. So it's like based on the correlation coefficient, we come up with this number that's always between -1 and 1. And actually, it will not change even if we scale all the numbers. It will give us the same number. That we do I actually prove it, or do I not? I don't think we prove it, but it's proven in the book, I think, maybe in the appendix. I didn't actually do it. But based on this definition, you can go and check yourself or look in the book if you care enough. And you'll realize that when we scale all the numbers, this number will actually stay the same. Right? And it's actually not hard to prove, because you know how when we scale the standard deviation, what happens? The scalar comes outside here. The same thing is going to happen outside here, and they'll cancel each other. Right? You can actually do that. Right? But that's the important thing, why we care about R. So this is a nice measure of how things are happening on average. The problem is, if I scale all the numbers, I have to redo all my calculations, because this number will change. So I don't like that, so I developed this number, which will actually kill any scaling factors that pop up. Right? And this number will always give us an answer between -1 and 1 inclusive. Right? In reality, the -1 and 1 pretty much never happen. That means all the points fall exactly on the line. Right? That never happens in reality. But there, in principle, it could happen. Right? If all your points fall exactly on a straight line, if it has negative slope, you'll get an R value of -1. If it has a positive slope, you'll get R value of 1, but everyone else is somewhere in between. Example. Correlation coefficient. This is also another very important definition, by the way. You're definitely going to be asked to compute this at some point. So I have the numbers here. Here's the standard deviation for x. I computed it. It is approximately 15.12357. Standard deviation for y. I computed that. That was 14.08072. This means that my R value is CXY over SX times SY, which is, I got the CXY last time over here, so I'm just going to plug that in. 163.22 divided by 15.12357 times 14.08072. And this ends up being, in this particular case, 0.766. A word of caution here. You see how for CXY we had to have the mean, and then for the R we have to have the standard deviations. More than likely they'll have you compute these yourselves. Right? So they're not always going to be given to you, just so you know. You should know how to actually compute them. Right? The formulas were given in chapter 7. Right? So sometimes they'll just give you a table of the data. You have to figure out the mean and the standard deviations and then find these guys. Right? Just so you know. Siri, how do we compute standard deviation? Based on 5 factors. This is why I went through that problem, so you can sort of have an idea why this happens. if a constant k is added to all x values, and you can base this from the formulas and the calculations we did last time. Adding a constant to all x values and another constant to all y values doesn't change the value of r. It's one of the reasons why we invented this value. It stays the same throughout all our shifting and scaling and adding. Right? If a constant k multiplies, so this is positive, if a positive So if all values of x are multiplied by a constant k, and all values of y are multiplied by another constant L, they could be the same, they don't have to be. The r won't change. Which is very nice. I mentioned this before, but I should put it in writing, it's that important. If r is close to +1, this means data shows strong positive correlation. i.e., the points are close to a straight line with positive slope. If r is close to -1, that means data shows strong negative correlation. That is, points are close straight line with negative slope. R is close to 0. That happens if data shows no or weak linear correlation. Other nonlinear trends. We're not going to focus on nonlinear trends, but they do exist. R is best for linear trends. I know this is a lot of writing, but like I said, chapter 8 is really like an intro to chapter 9. We have to get all our ideas and concepts together here, and then we can actually apply it to our statistics in chapter 9. And I did some examples here. Example. Some pictures here. In this case, there's X, there's Y. Right, see something like that? The best line to fit through them is like this. Such a graph, you'd say R is close to 1. You can have another case where you point like this. This is X, this is Y. In this case, R is close to negative 1. Something like this. So over here, you have points like a lot of them are in each of these regions. There's nothing clearly saying most are in 1 and 4 or most are in 2 and 3. So sort of just a horizontal line trying to capture everyone is the best bet. In this case, you say R is close to 0. Now, it turns out there are many ways that R can be close to 0. For example, I can have this trend. Here, again, a line going like this doesn't really capture what's happening in this picture, nor does a line going like that. So we're just like, just try to catch everyone. You'd say here, if you measure your R value, it would also, again, be close to 0. However, note, the last example. Notice that the line that would capture most points would just be a line going like this, which is not a straight line anymore, right? It's not linear. It's sort of parabolic. So it's sort of semicircular, parabolic. Right? Now, such trend lines exist, and you can actually do calculations, sort of figure out what curve best fits them, but we won't do that. We're going to focus on the linear case. Right? We're going to focus on, in chapter 9, we're going to call it linear regression. Right? We're going to learn about regression lines. Right? So things that we can measure with straight lines, that's what we're going to focus on. But I want you to be aware, straight lines aren't always the best to use. So it really depends on the data you have, and you can have more sophisticated trends that you can follow. However, in this class, we're going to focus on the linear cases, right? Things that we can match up with a straight line. And sort of anything that doesn't match to a straight line, in most cases, we'll assume r equals 0. But again, at the end of the day, you can split it into 4 regions and try to figure out where most points are, so you can know if it's slightly positive or slightly negative. Right? But in general, if it doesn't fit along a line, it'll be close to 0. But it can be slightly positive or slightly negative, and at that point, you just count the points, see which regions have the most on average. So, so you might be wondering, how do we get these lines? That's what chapter 9 is about. Right? So when we get to chapter 9, we'll do that. And an important idea here. The idea of correlation versus causation, right? You should note. I'm pretty sure that someone knows what I'm going to say. What is it I want to say about this?
Correlation implies causation.
Huh?
Correlation doesn't imply causation.
Right. Correlation does not imply causation. Now what you'll notice is with these trends, what exactly is it we're saying? We're saying as the x value increases, the y value increases, right? And here we're saying as the x value increases, the y value decreases, right? So something like this, when things share positive, strong positive correlation, what we're actually saying is when we get more of something here, we get more of something there. And so people might say, oh, this thing is related to that thing. If this thing causes that thing to happen. Because when these guys get more, those guys get more. And a lot of people make the mistake of jumping to the conclusion that correlation implies causation, which is in general not true. A lot of times there are unseen forces that our statistics can't get a hold of, at least with the measurements we're taking. And so we cannot assume that one implies the other. Right? So I've sort of in the beginning of this chapter, there was a quote. And I guess before actually going through this chapter, you probably wouldn't get what it's talking about, right? So the quote was, do you know that there's a direct link between the decline of the spiral graph and the rise in gang activity? Think about it. So basically what that person was saying, right? When one thing was getting smaller, like people were using less of this machine, gang activity rose. So he's sort of saying, well, you know, using less of this machine causes gangs to get bigger and better, right? So basically what he did was he plotted all these statistics, and he's like, okay, the less of this we use, the more gang activity there is, right? And there are websites that have all these curious correlation. So I'd like to sort of finish chapter 8 with that, where it says, there's actually a strong positive correlation between ice cream sales and violent deaths. Right, so if you actually plot ice cream sales versus the violent deaths of the year as the year goes on, when ice cream sales go up, Violent deaths actually go up.
Well, any death would go up.
Huh?
What
With
if
ice
any death would go up?
No, violent deaths specifically, right? So essentially, you know, every time you pop open that Haagen-Dazs, you're an associate to murder, basically. You are literally killing people by buying ice cream, right? Correlation implies causation. That would be a judgment call you would make. The more ice cream you buy and consume, the more people die. How dare you? You should be ashamed of yourself, right? I mean, you are literally making the world worse. There is actually also a correlation between importing lemons versus fatal traffic deaths, right? Traffic accidents, right? It turns out the more lemons we import from Mexico, the less traffic accidents there are. You can actually measure this. People can do the statistics and you can say, the more lemons we import, the less traffic accidents there are on the roads. So you know what? You should eat less ice cream and eat more lemons, right? Because correlation implies causation, right? So it's sort of an idea that you have to be careful about. So statistics is supposed to help us model reality and answer questions, but you can take it too far. There are limits to this power that we're developing, right? So you should be aware of that. Any questions on what we've done so far, by the way? Like anything didn't jive with you? So the idea is we had two-dimensional data and we thought, you know, using the x and y axis seemed like a smart way to actually plot this. So we plotted points, and then because we want to answer questions, we try to find a pattern. And so we try to find a pattern as far as signs go. We look at the standard deviation kind of thing with 2 dimensions. And we sort of developed this idea of patterns with signs. From that, we developed this idea of lines, and we sort of came up with numbers that would describe these patterns, whether they're positive or negative. It actually told us something. Our first stab at this, we got a number that changed when we scaled things or added things, and we didn't really like that because we want to be able to scale things without losing an idea of trend. And so that's why we developed the correlation coefficient R, right? And R actually directly relates to how well things fit to a straight line, right? So things that fit well to a positive line, our R value will be close to 1. Things that fit close to a negative line, the R value will be close to -1. Things that don't really fit to a positive or a negative line, the R value will be close to 0. There are some cases where a straight line is just not the right line to use in general, but we're not going to focus on that. Just be aware of it. You might do that in some higher classes. If you guys do biostatistics in some higher level class, you would probably encounter those. What else did I want to say? Right, so we're sort of going to use this idea. You can sort of see how the idea that R sort of coincides with slope. And so when we're trying to find the best fit line, you're going to see how R relates to the slope of this line. We're actually going to figure out a way to actually compute the exact equation of the line that fits all the points as best as possible. And why? Well, the idea behind that is if this one axis is like, for example, time, right? And we can say, you know, up to this point, this is the trend that's happening. What do we expect in the future? Right? You can sort of expect that the point is going to fall on this line somewhere. Right? So we can assume, okay, if we increase this, we expect this to happen, right? And so we sort of can make a prediction on basically the equation of this line, right? You plug in the x value, and then the y value is going to spit something out, and you're going to say, oh, if the x value is this, I expect the y value to be that. That's sort of where we're going with it. But chapter 9 sort of gets into that. Here, we just introduce you to the idea of how we can use lines to represent trends and sort of look at how one thing relates to another. So this one is saying there's one increase, the other increases, and so on and so forth. And we're actually going to take advantage of this and be able to answer a lot of questions in chapter 9 when we do regression analysis. But I don't know, I don't really want to start chapter 9. It's spring break on Friday. We'll just end early today. Unless there are any questions. So yeah, I know I owe you guys a lot of grades, like the tests and the quizzes. You'll get them after spring break. I'll probably send out your reports during spring break, so just stay tuned for that. And I guess see you in a couple weeks.